Okay, so yeah, we can start. So today we're going to talk about counting maps. Views on two yeah on the two sphere. So they're also called planar maps. Planar maps. So before I say much, so let me write down the problem and then. So this is the matrix integrals. Okay, so let's look at one example. Let Zn be equal to integral over Hn exponential minus n raised of 1/2 h squared plus gh4 dh. So this is a quartic matrix integral. Quartic matrix integral. And okay, so we know that this basically counts maps counts number of gluings of n fat flowers on a surface of genus G. Now I won't use G because that's a coupling constant. I'll just use H for various N and H. And so basically, this, if we write the perturbative expansion of this, as we saw, this is a double sum. The summation is over number of flowers that we take, and what genus H we want to have is a double sum, right? So this basically is a double sum over G and over H and N. But basically, the thing is obtained by gluing such fat flowers right? So as many you want, but when you glue them, you may get connected or disconnected Riemann surface of various genus H. The easiest thing is to do to look at connected ones, and in that case, we have to take log of this. So we just take log of this. We just count connected Riemann surfaces of different genus. But we also saw that by going into the double picture, we can get quadrangulations. So the number of tilings, basically, of this of surface genus G by quadrangles like that. So you have a surface of some genus H, and then you count in how many different ways you can tile this by quadrangles, by four guns. No, this is not good. So stuff like that. So what we do, we just fix N and H, and then we have some terms here. So that's what this Feynman diagrams for such matrix integrals told us in general. So counting or connected maps, tiles. So we just take log of this term. Okay, so right. Let W infinity equal to lim of n goes to infinity log of Zn log of Zn over n squared. And we know that this limit exists, and this basically gives us the planar. This W infinity counts planar, which it means spherical, basically. Tilings of a sphere with n quadrangles. Or equivalently with n fat graphs. Fat flowers. But this is an infinite series itself for various n. So yeah, right. So the normalizations that we use is the following: W infinity which of course everything is a function of this parameter G, W infinity G is a power series, formal power series in terms of this parameter G, which is sigma Cn, the coefficient we call Cn, and then there is minus G to the power n over n factorial. Okay, and begin equal to n. So again, the law is to make sure that we are counting only connected gluings of these things, so that we do get a connected only one Riemann surface. And these are all connected. There's no separation. And this 1 over n squared is necessary in order to get the limit. This is a scaling factor that's always for universal things. For large n's, this is always needed. So in this case, it's 1 over n squared. And this comes from the genus formula, basically. So the genus or topological expansion formula implies this. So now we know that there is this formula. So if we can compute this W infinity of G in a different way, then we can put it equal to this, and then we get the formula for Cn. So let me tell you what Cn is. So Cn is exactly that number we were looking. It's number of islands of the sphere. By, I believe it should be actually n plus 1 quadrangules. So for example, C1 is equal to 2, and C2, unfortunately, is very hard to compute by hand, is 36. But Cn, we get the formula for Cn, explicit formula for Cn, which I will write later. Maybe I'll just write it now. Yeah, Cn is equal to 12 to the power n, minus 1 factorial over n plus 2 factorial. So this result is due to Parisi, Brazil, or Berzan. It's its own Parisi and Zuber, the famous, very famous paper they wrote in 1978. This paper was motivated by Tufts' paper, which yeah.
Why is the power series minus G?
Sorry?
Why is it minus G to the power n?
Why is it minus G? Yeah. Oh, here there's a minus, and this is minus 1. And so the trick to compute this from Wick's theorem is to separate this term, quadratic term, from the quartic term, and then you raise exponential and the power series. So now we have to compute this quantity in an independent way in order to have a count for Cn. Because we know, so far, combinatorics tells us what Cn is, but by itself cannot tell us what is the actual value of Cn. Combinatorics only tells us the meaning of Cn, but the actual value of Cn, we have to use analysis. Some very interesting analysis. So I introduced new technique and a new transform, which is like an analog of, which is kind of sort of Fourier transform, but in this complex world. It's not really Fourier transform, more like Cauchy transform. And we'll see. It's a long calculation. I'll just give only the some essential elements of it. Okay, so on the definition, okay, ready this one. So the definition of W infinity, which we have over there, immediately implies that we can write it in a different form, which is W infinity of G is equal to EG minus E0, where EG is that is this lim of n to the power minus 2 log of Jn of G, Jn of G as n goes to infinity. So this Jn I not introduced, so now let me write what Jn is. Yeah, right, right. Jn is really like this log of Zn. Mm. Okay, so yeah, yeah, Jn is that expression. So now let us recall this Boyle's integration formula. Um, this Boyle integration formula allows us to write an integral over a set of matrices to an integral over a set of eigenvalues of the matrix. There's a big reduction because of the symmetry that's possible. It tells us that Jn of G is the following integral or n exponential of minus n. You see that quadratic term becomes sum of lambda I squared. Plus G is sum of lambda I to the power 4. You see, this term is trace of H2, and this is trace of H4 term, right? This whole thing is trace of H4. And then we have product of lambda I minus lambda J squared. I is less than J, d lambda. Okay, so this is the van der Waals determinant. And by the way, this should not be this should not be in the power. This is down here. I mean, you see, I hope there's no confusion. This is not in the power. This is down below. This is not. So, yeah. Okay. So this is Boyle's integration formula. It's not really called, so this implies this thing that we wanted there. Now, to compute such things, the standard method we talked about a long time ago is to use a Laplace approximation of, so the Laplace asymptotic expansion. So I will record it. This implies that actually EG is equal to maximum value of this integrand. The let me tell you why. So basically, what we are saying is that this limit n to the power minus 2 log of JG is obtained by finding the maximum value of this function. So there's a lot to unpack here. This is the function. Okay. So first of all, let us recall Laplace method, what it says as a first step. We call Laplace method. So as you may recall, it gives you an asymptotic expansion for exponential integrals. Gives the asymptotic expansion. Gives the asymptotic expansion. Exponential integrals. So in the following sentence, so we have that in the one-dimensional case, but similar thing is true in n-dimensional case. So if you have integral over r, exponential of minus 1 over h bar, f of x dx, we saw that this is equal to root h bar, yeah, exponential of minus f of c over h bar, I of h bar, where I of x, I is a function, a smooth function from there to r, such that I of 0 is essentially the value of the Gaussian integral that corresponds to the minimum of this function f of c. So let me write it. I of 0 is equal to root 2 pi divided by root f double prime of c. So here, f is a function, let's say, with a unique minimum, where f, so from r to r is, okay, has a unique non-degenerate minimum at C and fast enough growth at infinity such that the integral is, I mean, it's guaranteed that the integral is convergent over the whole R. So basically what we're saying is that there is a unique point where f prime of c is equal to 0, and that unique point, f double prime of c is positive. So this is non-degenerate minimum. So as you can see, this part corresponds to putting this function equal to its quadratic term only. This is the quadratic approximation for the function, and yeah, so this gives us the full asymptotic expansion. In particular, as h goes to 0, we can neglect all higher order terms and just keep I 0. So this would be the leading term. Okay. So in particular, as h bar goes to 0, the integral is well approximated by, root h bar into the minus f of c over h bar I of c. And that's what we want to do here. So here, n goes to infinity in this expression, n goes to infinity. This corresponds to 1 over h bar. So h bar goes to 0 is like n goes to infinity. And this whole thing here, so we can show that actually this function has a unique maximum, because now we're talking about the negative term. So let me write it here. Let k of lambda 1 lambda n be by definition just the integrand over there, exponential of minus n sum sigma lambda r squared over 2 plus sum lambda r over 4 times the van der Waals part. Yeah, I less than 3. So this is now we are taking the whole integrand instead of the power.
So there'd be a G on the quadratic term.
Yeah, there's a G there. Yeah, for sure. Yeah, G. Thank you. Yeah, so this plus G. So now claim is that, that's calculus now. This function k of lambda 1 lambda n is logarithmically concave. Like this. This is concavity. So it means that the second derivative of this function, so the Hessian of this function, k at any lambda is always strictly positive. So this is the second derivative. So this is this matrix. So this is a matrix, right? This is the matrix dk, d2k, d lambda I, d lambda j. As a matrix, this is a positive matrix. So this guarantees concavity, and there's a unique maximum follows from this. To do that, you have to take the second derivative of this guy and study this matrix. It's an interesting exercise, but it's not what we want to do. This is just an exercise, yeah. It's an exercise. So once you prove that, then there exists a unique maximum, which is pretty good. Brings us to that condition. There is one complication, though, that as n goes to infinity, in this result here, and similar results when you are integrating over some fixed space Rn, only the parameter changes, goes to 0, and we are approximating an integrand which is parameter dependent over a fixed space. Here, we are approximating a function which both depends on the space we are integrating on, because dimension is increasing. And here, this is also changing. So we have double parameters. So this is not directly applicable. I mean, so the Laplace method is not directly applicable. Nevertheless, people have worked this out and it's okay. So the best is a paper, is a book by Percy Dived. Limit exists. And the reference, the standard reference is the book by Percy Dived. It's called Random Matrix Theory of Human Hilbert Correspondence. Or something like this, and Human Hilbert Correspondence. Hilbert approach. That's a very precise book. It's excellent, and he exactly proves that limit exists in stage. So there's subtlety there, but essentially, I've been taken care of. Oh, here I made a mistake. I'm sorry. This should be negative. For the maximum, things should be negative. No. Okay, so once you do that, so you know that, I mean, the rest is just because we are taking log. Here we are really computing f of c. So the value of the function k at its minimum. So basically, we are really down to computing. And we get rid of this Hessian here, I of 0, because we are dividing two terms by each other. Because so that's also okay. So that's good. Now, so again, we have to find for the maximum points of this function. So the equation that we have to solve is the system of equation dk d lambda I equal to 0. Right? And if you write this down, this tells us that for I equal to 1 to n, so this tells us that sigma 1 over lambda I minus lambda j, sum over I, j different from I, is equal to n times 1/2 lambda I squared plus 2g lambda I cubed. Just taking derivative of this guy. But the interesting part is this thing which comes from the log of this guy, because we write this as exponential of log of these things, and the derivative of log is 1 over lambda. That's how this easily you get if you write this integral. So this is for Okay, so I should write J here. This is for I equal to 1, 2. Okay. So now as before, so consider the probabilistic, the distribution, the eigenvalue density function. Normalized eigenvalue density function as we did before, 1 over n, sum delta function x minus lambda I from 1 to n. So this quantity gives us the distribution of eigenvalues of a deterministic matrix H, one matrix, right? Now, what we want to claim, as in the case of semicircular law, the limit of such things as n goes to infinity exists, and it actually converges to a nice, almost everywhere smooth function. Again, that's not a very trivial theorem, especially in this case. So I just write the result, and the proof is part of this general book. So this is the theorem. This is again in Dave's book. That the counting measure yeah, 1 over n, sum delta x minus lambda I from 1 to n converges weakly to a measure, a probability measure. Measure mu of x. So actually, this probability measure is absolutely continuous in respect to the Lebesgue measure. So it has a weighting function, f of x and g, I call it, f of x and g dx, where we, okay, so where I should say f of x and g has support in an interval minus 2a and 2a minus 2a and 2a. This is smooth in a 2a and 2a and just vanishes at these two endpoints. So basically, it's going to look like this. So the support of this function, this counting, this limiting measure, going to be like this. So this is a symmetric interval minus 2a, 2a. Okay. So, yeah. You see, for G equal to 0, we have the Wigner semicircle, right? Remember, for G equal to 0, we have this. This is minus 2, 2, and it's like this. See? And I believe this curve should be symmetric anyhow, because of the symmetry in the problem. And minus 2a to a. And in general, this a is going to shrink. A is going to get smaller as G is positive, because this potential is pushing this gas of electrons, which are acting under the Coulomb law. This is like a Coulomb potential, a one-dimensional Coulomb potential. So it's a kind of attractive force. So it means that this is going to get smaller as G gets bigger than 0. But G also can go to less than 0. That's possible. Not all the way to -1, but there will be some interval less than 0 which G is accept. This analysis still works. Okay. So now the goal is to find this function. And then using that, we can find this function EG. And using EG, that we can expand it in terms of G, and then find those coefficients Cn, which are the power series expansion of the function. So, yeah, I mean, if we find this distribution, and then we can find this one, and then EG. Okay, so how we're going to go about this, finding this? And the key, in fact, is this equation here. Yeah, so let me now erase everything except this equation. Let's focus on this equation. I mean, the system of equations indeed. Then so these lambdas are points that are distributed according to some distribution for each finite n. But as n goes to infinity, this converges to that continuous distribution. And in that limit, then this equation tells us, so this is star, then star leads to as n goes to infinity, to an integral equation. For g of what was my notation for the limit function that I used over there? For the limit distribution, I had the notation. I hope I didn't use g. Yeah, I call it f of x and g. For f of x and g, so the idea is you just divide both sides by n, and then as you take the limit, this converges to Riemann sum, converges to an integral, and these guys converge to the value of the variable. So basically, then we get this equation. We get the integral equation is the following. So yeah, integral minus 2a f of x and g over y minus x dx is equal to 1/2 y, which is this one. Oh, this shouldn't be y squared. This is, sorry, 1/2 y plus 2g y cubed. Yeah. This is for absolute value of y. Yeah. So then to find the limiting distribution, we have to solve this integral equation, basically. So this expression here is a very well-known kind of transform, which is called, it has many names. So in general, let me write it. In general, so imagine you have a probability distribution on the line with compact support. If mu of x dx, in fact, doesn't have to be, I just write, if mu is a probability distribution with compact support on the line, it's still just or Cauchy transform or Cauchy transform is the holomorphic function so actually, instead of writing general, so let me write specific case that I have here. So f of x g. But the thing is very general, I mean, but that's okay. Let's just use it concretely. So imagine we have a probability distribution like this. So its Cauchy transform is the holomorphic function f of y. Yeah. Equal to integral minus 2a to 2a f of xg. This g is just a parameter for now, y minus x. Now this certainly goes from c minus 2a and 2a to c. So let's see what's going on. So we have this interval, right? And this is the support of the thing. Negative 2a, 2a. So we just excise this from the plane, from the complex plane, just throw it away. And then the rest with the x. I mean, is an absolutely well-defined function. And because the function 1 over y minus x is holomorphic in here, because this is just the inverse function, it's a holomorphic function, and we are summing and taking limits of holomorphic functions, and this is everything is convergent, absolutely convergent, it's very nice, because this is compact support, then this is a holomorphic function, which is defined here. Now, this holomorphic function is called the Cauchy or Stieltjes transform of this measure, probability measure f of x and g. Okay, so this is a great device. It's called the Stilges transform, and it actually connects measure theory on the line to holomorphic function theory. So it's a transform. So this Stilges transform is like a Fourier transform, but it's a different type. It's not Fourier, but it's Stilges transform. I mean, because measure theory it looks strange actually, because measure theory looks very different from holomorphic function theory. But through this, we can relate them. So basically, measure theory on the line holomorphic functions. In fact, more or less, this is one-to-one correspondence. Namely, we can characterize the set of functions that are obtained this way. I mean, certainly this function is injective. This transform is injective. If two measures with compact support have the same Stilges transform, they are equal. And we know exactly what holomorphic functions are obtained. Basically, all holomorphic functions that vanish at infinity, because at infinity, as we go, this is a bounded function on the line, but this goes to zero. So this is going to drop and goes to zero. Beyond these two things, there's a correspondence. And the thing is, we can also recover this function from f by going from above and from below. So this is kind of critical line that we have to exercise, but so there are a lot of things going on with this, but it is a whole universe. But okay. So in particular, now there is this famous Planar-Suchotsky formula, which gives you the inverse map, which we need. Yeah. Okay. The inverse map. So I will finish very soon, few minutes. This given line. And the Planar Suchotsky formula. Maybe why. So what is this? Basically, this tells us that so let me write it down. F of x and g is equal to limit of 1 over pi. Yeah, epsilon goes to 0 plus f of imaginary part, f of yeah, x plus I epsilon. So this whole thing is y now in this integration. Yeah. Okay. Go ahead. So this is the inverse. There is also a similar formula. So here, So we are approaching from above. There's also similar formula if you approach from below. You can also get a similar formula, but x minus I epsilon approaching from below gives you the formula. So we're going to use this formula for the inverse function, inverse math, basically to solve this integral equation. And once we solve it, then we can prove this it's exons over what is the all that formula. So I think we better stop now. Yeah. Any question?
F of x comma g, what is in the denominator?
Sorry?
What is that? Limit epsilon tending to 0 plus
Oh, this is pi.
pi.
This is this is pi. Yeah, this pi is from distribution theory. It's just there's an approximation to the delta function, which was actually obtained by Cauchy, and that's it. Yeah, in physics you learn different ways to approximate delta function. One of them is also 1 over x squared plus epsilon squared as epsilon goes to 0, right? I think this is what limit of this as epsilon goes to 0. I believe this is either delta function or some 1 over pi times delta function. Yeah. Have you seen that before?
Something like that.
Something like that. We must have seen it. Yeah, I'm pretty sure. In electrodynamics and many places, you must have seen that. Okay, so if there are no questions, I should say goodbye. So I will send an email today to for preparation of your talks. Hopefully, we start next week. And if you have any questions, please let me know. Send me an email. Okay, guys, thank you very much. See you on Wednesday.